Welcome back. Fifth lesson, nested quantifiers. Introduction. Here is an example of a nested quantifier. For all x, there exists y such that xy equals 1. So you see, for all x or for every x, that's one quantifier for every. And then there is here, there exists y. That's another quantifier there exists. So the term nested means quantifier within quantifier. Notice this particular expression can also be written as for every x, qx. What is qx? Qx itself is there exists y such that pxy. Now what is pxy? Pxy is xy equals 1. So you have for x, for every x, you have a statement. That statement itself is a quantified statement. Some well-known properties of real numbers can be explained using nested quantifiers. For every x, for every y, x plus y equals y plus x. That's the commutative law of for addition, for every x and for every y. The next one, for every x, for every y, xy is equal yx. This is the commutative law for multiplication. For every x, there exists y such that x plus y equals 0. This is existence of additive inverse. You see, for each x, there is a y. So notice this is very important. Order matters. For each x, there exists an inverse. That's what this is. For every x, for every y, for every z. So there are 3 quantifiers, right? X plus y first and then add z is same as y plus z. Add that first, then add x. This is what we call associative law for addition. Now translate into English. For every x, x not equal to 0 implies there exists y such that xy equals 1. Okay, so what I just said is the precise translation. For every x such that x not equal 0 implies, or such that, if you want, if x is not equal to 0, then there exists a y such that xy equals 1. Okay, you may use it in an if then setup, or you may simply say x not equals 0 implies the existence of a y such that xy equals 1. So this is simply talking about existence of multiplicative inverses, okay, for non-zero numbers, real numbers, say. We think of quantification as loops. The quantification for all or for every tells us to loop through every element in the domain and test the propositional function. Okay. Likewise, the quantification there exists tells us to loop through every element in the domain until we find some element which satisfies the propositional function. So we are going through the domain, checking every element in the domain. Note that the order of quantifiers is important. For example, for instance, for every x there exists y such that x plus y is 0. This particular statement is different from there exists. So notice, instead of here, there exists x such that for all y, x plus y equals 0. Well, look, for every x, there is an additive inverse. That's what this statement says. And this is a true statement in real numbers. For every x, there exists an additive inverse. That's different from saying there exists an x which is an additive inverse of every y. That's false. You have no x which is an additive inverse for every y, at least not in real numbers. Okay. What is the truth value of the statement? For every x, for every y, there exists z such that x plus y equals z, where the domain is set of real numbers. What does this say? It says for every real number and every other real number, where am I? Here. For every real number and every other real number, there is a z such that x plus y equals z. Of course, it's true. Z is the sum x plus y in real numbers. So for every x, for every y, you will be able to find its sum in real numbers. Now, what about the next statement? Next statement says there exists an x such that for every y and every z, x plus y equals z. No, this is false. Take any x. How can you guarantee that x plus every y will be every z? Okay. So for example, if x were 0, then z would have to be forced to be y. If x were 1, z would have to be 1 plus y. Yeah. Z can't be any arbitrary. No. Okay. So this one is a false statement. That's a true statement. Here is a table explaining quantifications of two variables for every x, for every y, pxy. That's same as saying for every y, for every x, pxy. What does this mean? It means pxy is true for every pair xy. When is this statement false? There is a pair xy for which pxy is false. Now here, next statement. For every x, there exists y such that pxy. What does this mean? For every x, there is a y for which pxy is true. When is this false? There is an x such that pxy is false for every y. You see? Next one. There exists x such that for every y, pxy. What does that mean? There is an x for which pxy is true for every y. What is the negation, or when is this false? For every x, there is a y such that pxy is false. There exists x, there exists y, pxy. What does that mean? There is an x for which there is a y where pxy is true. Likewise, there exists a y for which there is an x such that pxy is true. What is this? What is the negation of that, or when is this false? Pxy is false for every pair xy. Let Cxy mean that student X is enrolled in class Y, where the domain for X consists of all students in our college. domain for Y consists of all classes being offered at our college. Express the following state of each of these statements by using simple English sentences. So let's write that down. Okay. C. Randy Goldberg, CS 30. What does CXY mean? It means student X is enrolled in class Y. This means Randy Goldberg is enrolled in class CS 30. That's all it means. B. There exists X such that CX Math 32. What does this mean? There is a student X who is enrolled in math in class Math 32. There exists Y such that C Carol Setia in Y. What does that mean? Y is the class. There is a class Y such that there is a class Y in which Carol Setia is enrolled in and is enrolled. D. There exists X such that CX Math 32 conjunction CX CSI 32. What does that mean? There is a student X who is enrolled in Math 32 and in CSI 32. So that's what this conjunction is. X is enrolled in CSI 32, X is enrolled in Math 32, and, okay, let's go to E. There exists X, there exists Y such that for all Z, well, so you have a pair, X is not equals Y, and CXZ implies CYZ. What does that mean? If X is enrolled in class Z, then Y is enrolled in class Z. So there is a pair of students X and Y such that for every class Z, if X is enrolled in Z, then Y is enrolled in Z. So if this happens, then that happens. Next. There exists X, there exists Y for all Z. So you have a pair of distinct students such that you have, let me say distinct just to be clear. This is if and only if. So it's not if, it's not one-way implication anymore. It's if and only if. So let me copy and paste. There is a pair of distinct students X and Y such that for every class Z, X is enrolled in Z if and only if Y is enrolled in Z. That's what this is. Okay? Let's continue in our next video.